All right, once again, good morning to all. Hello, everyone. Welcome to our November 9th Monday plenary. Nice to see you all today. So firstly, I suppose a bit of congratulations are in order to you for having survived and I hope indeed thrived in our first two sections of this course. And today we're going to commence the third and last section, which is quite different from a departure from the other two. We are going to look at puzzles and paradoxes. Some of them are of initially internal concern to philosophers only, but I'm sure some of you will find them interesting. But as well, they have interesting applications, and particularly the ones we're going to look at in weeks 4 and 5 of this final section have a very interesting and diverse applications for everyday life. Although they begin as conceptual paradoxes, they will end as really trenchant problems. In fact, that large groups of people and arguably that the global village overall faces. So sometimes in philosophy, of things that begin as intellectual puzzles or challenges to our rationality will end up having profound applications to humanity as well. Obviously not in every case, but indeed in some cases. So this is our work, and I just want to preface this with a couple of remarks to you concerning puzzles and paradoxes and dilemmas. They fall into that category, some of them. I've been teaching this course for, about 26 years now at City College. And I introduced puzzles and paradoxes, usually just a couple of them at the very end of an intro course. We have more advanced courses in logic, which will definitely deal with some of those, and other courses in decision theory, which deal with others. But I thought for introductory students, it would still be interesting to look at a couple of paradoxes, some of the simpler ones, and I introduced them just for fun. And I discovered from feedback, basically from the classes, that the students really enjoyed them. Not everybody, of course, can't please all the people, but a majority of students found them interesting and enjoyable and even fun. And who'd have thought, that philosophy could be fun, but it can be. So when I was encouraged by student feedback, I gradually added more and more, and that's how we've ended up with 1/3 of the course, well, the final 5 weeks of the course devoted to them, primarily because I think they are interesting from the point of view of teaching tools, but also, and not less, because students do find them engaging. All right. And some of them more so than others, like everything else. Your textbook covers actually most of them, if not all of them, but in a very superficial way in some cases. So I will quite considerably enrich the presentation to you. All right. Because the recommended text is a bit thin on its treatment of some of them. But again, they're so well known that you'll find vast resources online if you want to follow any of them up for your final essay. Any of them in particular, you will find a plethora of resources. Some of them have been around for centuries, others for decades, but there's a lot of literature, believe me, and you'll have no trouble locating it. And I can also point you to some of it, okay? So that's just a bit of an introduction to where we're headed, kind of vague one, but I'm going to give you some very specific examples of some well-known paradoxes before we tackle our first set called Zeno's paradoxes. But I just want to back up my claim that there are many, many varieties, and I guess that this screen doesn't. I think you're going to see this backwards, right? But here's a book, really excellent book on paradoxes. If you're interested, I'll just put it in the chat room. There's one that's just called Paradoxes. I'm just going to hold up 3 books this morning. I pulled them down from my home library. I've spent quite a bit of time on paradoxes in my career. Paradoxes by R.M. I'm just going to give you the author, right? R.M. Sainsbury. And this is a publication. I think it's Cambridge University Press. Let me Just verify that. But this is a very well-known book, and R.M. Sainsbury, and indeed it is Cambridge University Press. So if you're interested in a really nice anthology of some of the most famous paradoxes and very brief resolutions, I think it's quite readable, although a bit technical in part. Another one is this one. It's a very nice paperback, and it's called Paradoxes from A to Z. And let me type that in. This is a bit more user-friendly, I think. A little less technical, but very challenging. Paradoxes from A to Z, or Z, as they say in British English, okay, from A to Z. And that's by Michael Clark. So that's another book that you might find useful or interesting if you want to delve into them. And the last one, this is by no means not all, but this is called Paradoxes of Rationality and Cooperation, because it turns out that paradoxes can be found not only in logical domains and in set theoretic domains and semantic domains, but also in social and political and economic domains. They're rife with paradoxes. And we're going to be looking at two very famous ones in a few weeks, namely the prisoner's dilemma and Newcomb's problem. They're upcoming. And this is a really interesting book of essays that are very, very technical, but it treats them. And let me just type that in for you for the sake of completeness. This is a really marvelous book dealing with Newcomb's problem and the prisoner's dilemma, paradoxes of rationality and cooperation is the title. It's a collection of essays. And the authors are Richmond Campbell. I'm typing this in. Richmond Campbell and Lanning Sowden. So I'm typing those names in. Lanning Sowden. So there you go. And I think that Sainsbury's English, Michael Clark might be American. Since this is Routledge, could be English as well. And Campbell and Sowden, I think, are Canadians. But in any case, philosophers worldwide are interested in paradoxes. And indeed, you could spend your career studying paradoxes and possibly never get to the bottom of some of them. I've solved a couple of difficult ones in my career. And I'm sort of almost proud of it, but it took a lot of thought, took many years to get to the bottom of some of them. Okay, we're going to study some in this section of the course, and we'll be able to get to the bottom of them much more quickly. They're going to be simpler, but I hope not less fascinating paradoxes for you. All right, so first question, I guess, from me to you would be the following. What is a paradox? All right, you probably all heard the word. There's even a town upstate New York called Paradox. Did any of you know that? It's in the middle of the Adirondacks. I think there's a lake Paradox, and there's a town called Paradox, New York. I always wanted to retire there. I thought this would be a great place for a philosopher to live, don't you think? I'd love to be able to give my address as Paradox, New York. But anyway, so your answers are coming in now. Great. Okay, a contradiction. That's correct, Mona. It is in some sense a contradiction. It's self-contradictory. Could be self-contradictory. Yes. Nicoine, very good. Nicoine could be contradictory, right? Or is that Lenise? Yes, that's Lenise this morning. Raquel, when something contradicts itself, yes, something has a double meaning. That would be more of an ambiguity or an equivocation, Ahmed. We call that an equivocation when it can be taken two ways, or, but we're not sure which way it's intended. But I think you're all on the right track. It's obviously something that's problematic in some fundamental sense, and most of you are using this word contradiction. That's not always the case. So let me give you what I would consider to be perhaps a closer definition. I'm going to share a screen with you. It says you're all on the right track. let me just share a screen with you about paradox, give you a definition and explanation of what it means to resolve one in general, most generally, before we get down to Zeno. Also, the price we pay, interestingly enough, whenever we resolve a paradox, there's a little price or maybe a big price, often an epistemological price that we pay. And maybe some of you haven't considered that. And as well, I want to then give you some quick examples of some well-known paradoxes, and we can have a look at why. And you will see in those examples exactly what some of you have asserted just now, that there is something perhaps inherently contradictory about a paradox. So that's a very good intuition or experience. So let me share the screen with you, the first screen for today. Just bear with me. And we have this screen called paradox. All right. A paradox is an argument or a deduction, some kind of story, right? But more formally, an argument that leads from apparently rational or logical premises to a seemingly impossible, or in other words, what we call paradoxical conclusion. So it's not necessarily always a contradictory conclusion, but it's certainly counterintuitive. For example, Braze's paradox in transportation networks illustrates that sometimes adding an extra node to a network with the intention of freeing up congestion actually results in increasing the congestion, whether you're talking about a network of roads or a network of data communication or anything that's conveying something along a network. You can end up causing a worse problem by trying to resolve one. And it's paradoxical that if you add alternate routes, you can increase congestion. But that's what happens. So it's not always contradictory, but it can certainly be puzzling, or indeed apparently inexplicable, or maybe even impossible. Yeah. And can also indeed be contradictory. All right. So a paradox, generally speaking, if we want to ask really how does a paradox arise, in most cases, one could argue it arises because of some flaw in at least one of our assumptions, or our premises, or our assumptions in the model, right? And or an error in at least one of the background assumptions supporting our premises. So maybe the things you're assuming are not transparently false or flawed, but there might be an error lurking in the background. And this is what we call an implicit as opposed to an explicit error. But this will still end up affecting the result. Okay. And the conclusion really comes from a flawed assumption, either in the actual premises that lead to the paradoxical conclusion, or indeed in the background assumptions that inform the premises. Okay. So our job and how we resolve a paradox is by always going back to the argument, going back to the premises, and trying to identify which one of them or ones of them is flawed, right? Or flawed. There must be some faulty premise, or perhaps more than one. So we need to identify those and then correct the flaw. And that usually resolves the paradox. But as I mentioned, we'll pay a price for doing this. And the price we pay, interestingly, for resolving a paradox usually necessitates a change in our common sense or taken for granted understanding of things. Because a paradox arose, one could say, or arises in the first instance because of a misunderstanding, some fundamental misunderstanding. And so correcting the paradox, or resolving the paradox rather, will entail correcting our misunderstanding. And so we will understand things in a new way, and then be obliged to change, forever, whatever the erroneous background assumption was, or the erroneous premise. All right. So it will make a shift happen in the way we look, not only at that problem, but maybe even at the larger world. And if you want to resolve a paradox, then you have to be willing to make that kind of cognitive shift. All right. Or maybe an epistemological shift. And that's not often discussed, but this is really one of the after effects of the method itself. And paradoxes arise in many domains. And I've given you 3 books just as an example. And there are many, many other domains that I haven't talked about, where we encounter paradoxes. Okay, is that clear? So should we have? If this is clear, we'll go on to some simple examples of paradoxes. Everybody happy with that so far? Any questions? I'm just looking at the chat room if I can. Everyone's good. Okay. We can proceed. All right. Very well. Thank you for your feedback, Jana, Hillary, Ahmed. Clear. All right. Let's carry on then. I'll keep the chat room open, obviously, so we can proceed, because now we're going to get down to some cases. Again, the menu this morning is we're going to cover. I'll just type this in. We're going to look at Zeno's, 3 of Zeno's 4 paradoxes this week. That's the main objective. We're going to look at, now you may sometimes hear me say Zeno, and you may sometimes hear me say Zeno, okay, Z-E-N-O. If you're in the U.S., if we're in the U.S., of course we pronounce it Zeno usually. If we're in the UK, speaking UK English, we say Zeno. It's like zebra and zebra, okay? Z and Z. The letter's the same, spelling's the same, pronunciation's different. I'm sort of bicultural, so I may mix and match, but I'm talking about the same guy, okay? Zeno of Elea, not to be confused with Zeno of Citium. Zeno was apparently a common name in ancient Greece. Zeno of Citium was the founder of Stoicism. Zeno of Elea is the one who left us these paradoxes. All right, so we're going to look at them, but beforehand, let's look at some illustrations of at least 3 kinds, which are related perhaps, but we're going to look first at a computational paradox. And if you want to burn your computer out, you can do this. We have 2 sentences. Sentence 1 says, the following sentence is true. And sentence 2 says, the preceding sentence is false. Okay, 2 simple sentences, somehow related because they're making claims about each other. But then we ask a question, is sentence 1 true or false? We could also ask the same thing about sentence 2. Is it true or false? And you could program your computer and then ask it to, computationally to assign a truth value and determine it. Well, here's the paradox. I mean, this is what's paradoxical about this is the following. Let's look at sentence 1, and let's say for the sake of argument that sentence 1 is true. Okay? So sentence 1 says the following sentence is true. And if that is true, as we're assuming it to be, then is sentence 2 true or false? If sentence 1 is true, then what is sentence 2? Is it true or false? Come on, are you with me this morning? Type it in. If sentence 1 is true, on the assumption, yeah, that's right, Ahmed, on the assumption that sentence 1 is true, then sentence 2 must be true. Sentence 2 must be true, because that's what sentence 1 asserts, right? Very good. Of course, not a guess. It's logical. This much is not guesswork. Of course, sentence 2, on the assumption that sentence 1 is true, of course, sentence 2 is true, because that's what sentence 1 asserts about it, okay? But here's the problem. If sentence 2 is true, all right, sentence 2 asserts that the preceding sentence is false. So if sentence 2 is true, then is sentence 1 true or false? On the assumption that sentence 2 is true, yes, exactly. On the assumption that sentence 2 is true, then sentence 1 is false. But wait a second. So how can sentence 1 be both true and false? Right? But let's continue to play the game for a minute. If sentence 2 is true, then indeed sentence 1 is false. But then if somebody says it's too early for this, yeah, have a cup of coffee. I'm going to shake your neurons this morning, okay? This isn't the LSAT. I think it's been abolished. This is worse. Some of these paradoxes are not resolved. We just have to accept that with some of them there's something wrong, but there's no agreement among philosophers. Though, Hillary, it's too early for your head to be hurting. We're only looking at the first example, okay? So take an aspirin or something, and come back, because it's gonna get worse before it gets better. All right. Okay. So remember where we are now. Don't try and derail me. I'll just make you more confused. Some of you already. But if on the assumption number 2 sentence is true, the first sentence is therefore false. So if sentence 1 is now false, okay, the sentence 1 is false now. We've demonstrated that it must be. If it's true, it turns out to be false. But if sentence 1 is false, it's asserting that sentence 2 is true, right? But if that's false, then sentence 2 must be what? True or false? It's right. It has to be false because sentence 1 is false and it's asserting that sentence 2 is true. So therefore, sentence 2 must be false. But sentence 2 was also true the first time around and now it's false. But if it's false, it's claiming that the preceding sentence is false. But if it's false that the preceding sentence is false, then the preceding sentence must be what? True, exactly. Excellent. Okay, now you guys are with it. So now we've reached what? We've reached an infinite loop. Okay, we've reached an infinite loop. You see, computationally, are some of you involved with programming, computers by any chance? Is anybody doing any programming? Any kind of, no, all right. Well, you see, this is what's going to happen. Oh, you are Brandon. Okay. But if you program a computer to solve this, it's going to be caught immediately in what we call a tight infinite loop. It's never going to be able to answer that question because every time it tries to answer that question, it's going to keep cycling through what we've just cycled through, except at very high speed, right? It's going to find out that if 1 is true, 2 is true, but if 2 is true, 1 is false. All right. But if 1 is false, 2 is false. But if 2 is false, 1 is true. So that's one loop. And it will just keep looping. It will never stop. It can't answer the question because it will be in a tight infinite loop. So you see why the ancient Greeks were suspicious of infinity? They weren't wrong because these tight infinite loops don't resolve anything. Presumably your computer would only stop if you halt the program or if the hard drive burns out eventually, right? Or if the universe reaches a state of maximum entropy. This loop could go on for trillions of years if undisturbed, but we never get an answer. So, okay, now would a Turing machine be able? Well, no, Ahmed. I mean, a Turing machine can only do exactly what we've just done with words, which is to cycle through the logic, right? The Turing machine is only translating computationally through TTL logic, basically, what we've just argued in the English language. It's just going to do it with symbolic logic, Boolean algebra, but it's not going to be able to resolve the question because the question in fact can't be. So now you understand that this is why this is paradoxical, because indeed it's self-contradictory, as some of you asserted earlier in general, because a sentence obviously that turns out to be true at one moment, it turns out to be false at the next part of the cycle, and then true again, and then false again. Okay, so what is the background assumption that we have to correct? Well, I'm not saying the paradox can be resolved in terms of the question being answered. Obviously, will never be answered. But there's a background assumption that we are smuggling in, which makes the whole thing perhaps more perplexing than it needs to be. Okay? So what is the assumption? Can anybody identify? What assumption have we all made that has kind of led us into this computational trap from which there is no egress, yeah? No way out. What's the assumption? Any ideas? That you're very close, Dahlia. Good guess or good intuition that a sentence. Well, no, we Alejandra, it's true that we explicitly assumed sentence 1 is true. I mean, that was an assumption we made, but that's not what I'm asking. I'm asking a different question. I'm asking about an implicit assumption in the background, something that informed, yes, that's much better. Ahmed, you're on the ball as often you are, the assumption of what is true and what is false. And more specifically, I think we can even rarefy that and say, we've assumed, have we not, when approaching this problem, we assumed that every declarative sentence must either be true or false. I mean, in general, don't we assume that a declarative sentence is true or false? So like if I say to you, okay, today is Monday, that must be true or false. Obviously, if I say, that it's Monday today, you'd say, yeah, it's true. But if I said it's Tuesday today, you'd say, no, that's false. So, or my name is Jones, right? And so forth. So yeah, necessarily understood that we go through life. Don't we normally go through the day, at least, mostly assuming that declarative sentences are either true or false, and that there isn't any other option. Right? And this goes back to Aristotle. He did some formative work on this kind of logic, and it was he who really, he gave us a famous saying, tertium non datur, that there is no middle. Okay, there isn't anything in between. Of course, in quantum physics, we get the paradox of Schrodinger's cat, which is maybe neither dead nor alive, but in a superposition of states. I mean, there are some paradoxes, many paradoxes of modern physics, which also will shake up this assumption that it's not necessarily the case that every declarative sentence is either true or false. Okay. And that leads to other really interesting problems. But if we are willing to relinquish the base assumption, in other words, and admit that not every declarative statement is necessarily true or false, or necessarily determinably true or false, right? I mean, maybe there is truth or falsehood in the nature of things, but there may be some epistemological barriers or a computational or other kinds of barriers which actually prevent us from knowing what's true or false. That's a different kind of problem. But in this case, if we jettison the assumption that every declarative statement must be true or false, then we're not going to be particularly perturbed by this computational infinite regress. Okay, so we don't, we haven't answered the question, but we've, in a certain sense, resolved the paradox. Okay, fair enough. Okay, everybody more or less happy? More or less. All right. So let's go on to the second example. So could I re-explain that? Well, I can try. What I'm saying is what I said in the first slide, that sometimes the price we pay for resolving a paradox can necessitate some change in our common sense or taken for granted understanding of things. Yes, we resolve a paradox by identifying either an explicit flaw in one of the assumptions, or indeed an implicit flaw in one of the background assumptions that we brought to the argument. And in this case, the computational case, the apparent paradox arises because we are assuming that every declarative statement must be either true or false, and that no statement can be both true and false at the same time, or quickly in an alternating sequence. But going through the computation as a Turing machine would, we've stepped through it and we've seen that number one turns out to be true momentarily, and then on the assumption that it's true, it turns out to be false, and on the assumption that it's false, it turns out again to be true. So we just see it cycling between truth and falsehood, and so is sentence two for that matter. They're neither true nor false. They will continually cycle between apparent truth and apparent falsehood because of their interrelationship. So if we abandon the assumption we brought to this thing implicitly, that assumption being that every declarative sentence must be either true or false, if we abandon that assumption, then we really, in a certain sense, are not going to see this as paradoxical anymore. Okay, Linnies, that's my attempt to re-explain it. All right, now we'll move on to this is worse. Okay, the second case actually worse. This is a variant or a very simple formulation of something called the liar paradox, and there are dozens and dozens of versions. This has also been around in the literature for, I think, since ancient Greece, and I know since ancient Greece. I mean, I wasn't alive then, but it's in the literature. It's called the liar paradox. And this is only one sentence, but we don't need two. We can generate a paradox with one. Suppose I say, and I put it in quotes, okay? Suppose I say to you guys, okay, I'm lying to you. All right? Like someone's saying this, right? I'm going to put it in the first person. I'm lying to you. I've just said that in quotes. I'm lying to you. Okay. So suppose I'm telling the truth. I mean, suppose I am lying to you, right? Well, if it's true that I'm lying to you, then actually I'm lying to you about lying to you, am I not? If I really am lying to you, then in fact, I'm not lying to you at all. Because if it's true that I'm lying to you, then the statement I am lying to you is also a lie. And if I'm lying to you as a lie, then I must be telling you the truth. So if I'm lying to you, I'm actually telling you the truth. Okay. So wait a second. Now apparently I'm telling you the truth, but excuse me. If it's true that I'm lying to you, right? Then I really am lying to you, right? So what I'm saying must be false. But if what I'm saying is false, hang on. If what I'm saying is false, then if it's false that I'm lying to you, then I must be telling you the truth. So in other words, if I'm lying, I'm telling the truth, and if I'm truthful, I'm telling a lie. It is partly a semantic paradox. That's indeed one way of looking at it. But you see, it bears a certain similarity to the computational paradox, because it's impossible for a statement to be both true and false at the same time. So we would think, right? Could it be possible that you're lying about something else, but not necessarily? Well, that's a really interesting question, Alejandra, and this depends. And some of you were thinking along those lines. Yes. Well, there's another variation, okay, but it's self-referential. The real key to this being paradoxical, I like that some of you are somehow intuitively on a very constructive track here when it comes to penetrating the mystery. I think one of the main early formulations, I'll just type it in, Epimenides, which is the name of a person, right? I'm typing this, Epimenides the Cretan. The Cretan is somebody from Crete, okay? Epimenides the Cretan said, and I'm putting this in quotes, he said, this is another version of this, he said, all Cretans are liars. Okay, so this is an earlier or a different version of the liar's paradox. Epimenides the Cretan said, I've just put it in the chat room, Epimenides the Cretan, in other words, he's a person from Crete. He said all Cretans are liars. Well, excuse me, he's from Crete, right? So if he's from Crete, he's talking about himself too. So if he says all Cretans are liars, then he's also a liar when he says this. Okay, which means if he's a liar when he says this, then maybe he's not a liar at all. All right, so this is an earlier variant. All these things are variants on the liar paradox. And so now Ahmed asks, if I told you a lie, then I told you I'm lying to you, then isn't the lie still a lie? But my statement, I am lying to you, the truth. Well, Ahmed, this is a really great question. If you say to me, Ahmed, I'm lying to you, right? If it's true that you're lying to me when you say you're lying to me, then how can I be sure you're lying to me? Because if you're lying to me about lying to me, then you're not lying to me. You need more caffeine. Okay, if some of you need at this point a coffee break. I'm glad that logic in this case is prompting you to want to think more carefully. It does for all of us. This paradox, I want to give you a sense of relief that as I said, the liar paradox has many variants, many variants, and that they are still being debated. I mean, philosophers love to debate. But really, there are different interpretations of why the liar paradox is a paradox and how one might be able to resolve it. It's very, very complicated and very widespread in terms of its discussion in the literature up to our present day. So that's just, I've given you a very simple version of it. Okay. But again, I would argue, just for our basic treatment, that one of the problems with it and one of the things that makes it paradoxical is this whole notion of self-referentiality that some of you already pinpointed, and that we see a common denominator, therefore, between the computational paradox and the liar paradox, that part of the problem arises when the statement or statements under analysis are either referring to each other or referring to themselves. You see that? If they were not referring to each other or referring to themselves, it would be simpler, arguably, to discern their truth or falsehood, or as we say in logic, their truth value, and quite plausibly the paradox itself would disappear. Okay? So like jumbo shrimp, yes, this is a typical one, Hillary. I see you're active on the web this morning too. You're multitasking as usual. That's great, and that's true. I mean, that's what we call more of an oxymoron, a self-contradictory statement, right? A jumbo shrimp. We know that that a shrimp is usually a small thing, and in colloquial English, to call somebody a shrimp. I don't know if we do this anymore. When I was a kid, we used to tease people who were perhaps very, very slight in stature and call them shrimps, meaning they were small. So the whole idea of a shrimp is a small thing, right? So to call it a jumbo thing is, of course, ridiculous. It's not a paradox. It's a contradiction in terms, right? More of what we call an oxymoron, meaning a contradiction in terms. That's related, but it's not particularly paradoxical. We're just juxtaposing, in this case of a jumbo shrimp, we're juxtaposing two sort of self-contradictory notions, okay? But definitely a bit puzzling to do that. All right. Now, the last one before we get to Zeno is, as I said, a very famous set theoretic paradox. There's a much more sophisticated version of this, which I'm going to spare you because it really will twist your mind into knots. But what I'm giving you below is a much simplified but equally entertaining, maybe more entertaining version of something called Russell's paradox. And if you Google Russell's paradox, you'll get the original, fairly sophisticated version that has to do with set theory. This is Bertrand Russell, the great British philosopher of the last century, who once was hired by City College, also a Nobel laureate, Russell, I believe in literature, and a very famous and great philosopher, not only a logician, but very well known as a logician, but he did many things. He was also socially and politically active. And as I say, was hired by City College to teach during the Second World War when he was stranded here in the U.S. And then his position was overturned by New York in a total act of political persecution. Very interesting story. So anyway, one of the great philosophers of all time, we had him temporarily in our faculty. He signed the contract, and then he was ganged up on by the New York Times, the mayor's office, the Episcopalian bishops, the Tammany Hall politicians, and a bunch of other people. He was canceled, basically. Didn't apply. That term didn't apply in 1940, but he was canceled. And he never taught a day. He never gave a lecture at City College, although he was technically on our faculty for a short time. A very interesting story. That's not much what he's known for. He went on after the war. He went back to England and went back to Cambridge and did amazing things. And Ahmed said that's why philosophy is mind-boggling at CCM. I know not because Russell was hired by us, but because philosophy is mind-boggling everywhere, Ahmed. I don't think it much matters. We don't have a monopoly on what's mind-boggling, okay? If you delve into various nooks and crannies of philosophy, I'm guaranteed your mind will get boggled. But this is one of my favorites. I'm sure you'll find this one amusing, okay? And this is an allegory. This is only an allegory on Russell's more formal paradox. But it's imagine a village barber, okay? Suppose there's a village, and the village has one barber, okay? And suppose the barber shaves everybody who doesn't shave himself. All right, that's what the barber does. That's what barbers do. So if you don't shave yourself, you go to the barber, right? And the barber shaves you. But suppose you do shave yourself, you shave yourself at home. So then you don't need to go to the barber because you shave yourself. So if you shave yourself, the barber doesn't shave you. That part's easy. I mean, that's not controversial or paradoxical. But now comes the question, as you are all going to see it coming by now, right? Does the barber shave himself? And now we land in a full paradox, because according to the conditions of the argument, the barber, well, Aisha, we do know. We can do the logical deduction. We've already said that the barber shaves everyone who doesn't shave himself, right? So if you don't shave yourself, the barber does shave you. And if you do shave yourself, the barber doesn't shave you. So the village only contains one barber. You can't dodge the question, Asha. There's no other barbers. So we've got to focus on this barber. It's the only barber. Okay. There's no easy way out. And now we just apply the conditions of the argument. Okay. Does the barber shave himself? Well, if the barber shaves himself, then obviously, according to the argument we've just given, he doesn't, because the barber shaves only those who don't shave themselves, right? So if the barber shaves himself, he doesn't shave himself. But on the other hand, if the barber doesn't shave himself, then of course he does, because by definition, the barber shaves everyone who doesn't shave himself. So if the barber doesn't shave himself, then he shaves himself. On the other hand, if the barber shaves himself, then he doesn't shave himself. And surely that's a paradox. All right. Okay. Well, Ahmed, I want to underscore to you that a paradox does have a final answer, and that every paradox that has thus far cropped up in the history of thought, whether it's logical or scientific or otherwise, there are psychological paradoxes, there are all kinds of paradoxes. The ones that have been solved are all shown to have answers. These books that I showed you earlier contain paradox after paradox that has been resolved, and the answers are given clearly. But please don't lose sight of the first slide in this 2-slide set, namely that there's a price. That when we resolve a paradox, it means we also have to modify something in our assumptions, either about the actual premises in the argument that led to the paradox, or in our background assumptions that actually gave rise to the premises themselves. So a paradox is something that sometimes has been conclusively resolved. At other times is still being debated, because people are perhaps running competing resolutions and don't agree on the best way to resolve it or the final way to resolve it. Or it remains unresolved because no one has yet come up with a resolution. So there's three, putting up 4 fingers, there's 3 possibilities. Okay, one possibility is that it's been resolved to everyone's satisfaction. Secondly, it's been resolved, but they're in more than one way. So people may be debating, which way is actually a better, somehow, or more convincing resolution. And thirdly, maybe it hasn't been resolved at all. So people are still thinking about it. All right. So a paradox, by definition, it's like a crime. I mean, I'm not saying that it's a crime, but we want to solve crimes, right? And sometimes we have cold cases where no one can come up with the crimes, at least the solution, to the crime. But it still means that something went happen, but we don't know what. And a paradox, you could say, is like not a crime, but it's a little bit analogous, because it's a case that we want to solve. So we're going to all be detectives, philosophical detectives, and try and figure out what's wrong. What went wrong in our thinking, not criminally, but logically or rationally. And if we can detect what went wrong in our thinking, we can set it right, and then we can indeed solve the case. Okay, so now we have some people. So does the barber shave himself? Well, Ahmed, that question is just what is paradoxical, because what we've said is we've seen that the barber, if the barber shaves himself, then he doesn't, because he only shaves those who don't shave themselves, right? But on the other hand, if he doesn't shave himself, then he does, because we've seen that, again, he only shaves those who don't shave themselves. So this is the paradox. So that's not, there's no resolution on the table yet. And Edward said you used to go to a barber with 3 fingers when you were. Well, I would avoid, not to discriminate against people, but I think I would avoid getting shaved by barbers with fewer than a full complement of fingers. Maybe he was born that way, or maybe he lost them in an accident. But it certainly would be poor salesmanship to be I think to be shaving people if you didn't have a lot of fingers. Maybe people would wonder how you lost them. Okay, so now let's get back to the problem. You see that, okay, well, maybe he was pretty good. I guess he had a lot of practice, right? Okay, maybe he made all his mistakes on himself, Edward. But in any case, here's the thing. Looking at this, we realize that this problem is not a problem if we exclude the barber, all right? For everybody else in the village, it's not paradoxical, correct? If we think about everybody else in that village, either the barber shaves them or they shave themselves. There's no problem, right? No problem. The only time we're getting into hot water here, the only time we're creating a paradox out of this is if we ask it about the barber himself. So if we include the barber in, if we look at this as a set of people, who are either shaving themselves or being shaved by the barber, it's only when we try to include the barber in that set that we generate a paradox. This is why it's a set theoretic paradox. And actually, Russell's solution to it, if there is any solution to it, it's telling us that there's something embedded in the axioms of set theory. And I'm not going to go there. This is an advanced topic, but the actual technical solution, one technical solution would be that there are certain rules that we have to abide by in terms of the way we assemble sets or collections of objects. And if they become self-referential, that is, if they include themselves as elements of themselves, then we're indeed prone to run into problems like this, which don't prima facie have any solution. So a way of preempting the problem is not to allow sets to include themselves as members, and that's a more technical kind of solution. But don't worry about that. I'm not holding you accountable for it. I just wanted to point out that if we naively run around, and I think that this is a takeaway from this paradox of set theory, however it's couched in technical language or in allegorical language. If we run around assuming that we can assemble sets of things arbitrarily, then we may end up in paradoxical territory. You see, a set is just a collection, right? A set is just a collection of objects, and it's totally non-specific. It could be a set of real things, like if you are beach combing somewhere. I wish I were sometimes with this lockdown. We can't go far, but if you're beach combing, collecting seashells, it's a set of seashells. You pick up seashells and you have a collection of seashells, and it's a set of seashells. And you would think arbitrarily you could certainly collect any seashell you want or leave it on the beach, right? Environmentalism aside, endangered species aside, if you can add to your collection or discard from your collection any member at your convenience or your choice, and there's no paradox there. Same like collecting stamps, or whatever you want to collect. But it turns out that certain kinds of collections will present paradoxes just in case the elements of that collection are themselves the set. And this is not explicitly this allegory a case of that, but it's a case that points to that problem. Russell's paradox explicitly is that kind of problem. So it turns out that we can't arbitrarily form sets without potentially running into paradoxes. And that poses some limitations on actually what we're able to do when we want to manipulate collections of objects for mathematical or logical purposes. Okay, so we'll just leave that to you for now. You get the idea by now clearly of what some examples are of paradoxes and how perhaps we can approach them. So we'll come to Zeno, and Zeno gave us 4. I'm going to treat 3 of them with you. 1.5 today and 1.5 on Thursday with my breakout group. And then we're going to see perhaps what kind of background assumptions we have to change in order to resolve Zeno's paradoxes. I'm going to stop the share right now. Oh, there's somebody on the beach. There you go. Very nice, Alejandro. That's looks like a really nice beach. And I hope we'll be able to get back to the beach before too long. Right? Vamos a la playa, right? Is that what we say? Vamos a la playa. Okay, in our dreams right now. Thank you for sharing. Okay. All right. We better get back to Zeno. I bet it was a nice beach. Where was it? Far Rocks. Okay. Very nice. Let's return now to Zeno. Yes, paradoxes of motion, Nicole. Good. We're back on the track. So Zeno had a particular motive in concocting these paradoxes, because transparently we know from our experience they're all going to be false. we know what they're asserting is ridiculous. So the point of Zeno's paradox is not to produce something that is really not in common sense refutable and from everyday experience refutable, but it's rather to challenge us to explain where does he go wrong in his logic, where is his argument going wrong. Because it seems that what he's concluding, this is the classic definition of a paradox, yeah? That it's an improbable or an impossible conclusion that arises from seemingly very plausible arguments. So Zeno really made people think, and that's why we're still looking at him today. He's going to make us think too in a moment about paradoxes of motion. And that's right, Nicole, as you say, Zeno's paradoxes are all about motion. They all deal with motion one way or another. And he was questioning this notion of how is actually motion possible? How is it possible for things to move, not only through space, but as we'll see later, also through time? And this is not a simple matter. And when you begin thinking about it, you may realize that our common sense views of motion are not necessarily exactly how motion works. And that's what Zeno is on about. He wants us to think more carefully about what it means for something to move. And his paradoxes all made us think more carefully about motion. And in fact, some of them were not resolved for centuries because we didn't have enough mathematical machinery. We needed 19th century analysis, actually, to resolve the second one that I'm going to show you. First one was known to the Greeks. And we really also didn't get a clearer resolution of it until the 19th century with Cantor's transfinite arithmetic. Now, don't panic. I'm saying this to you because in the history of mathematics, it's just verifiable. But you don't need anything more than high school math to do this. So, if any of you had high school math, you will not have any problems with the math we're going to look at. It's only high school math. If some of you spent too much time on the beach, however, like this beach, and I'm not saying you, Alejandro, I'm just saying if anybody spent too much time on the beach and not enough time with high school math, then maybe you'll have a struggle, but conceptually, at least, you should be able to understand what's going on. These paradoxes can all be explained without mathematics, although sometimes mathematics is a manner of notation which makes explanations more compact and therefore easier for us to grasp. So let's look at the first paradox.
Before we can go to the paradox, I have a question, Professor.
Please.
You said that Zeno questions motion, but isn't this paper like to defend his teacher's theory about like motion does not exist?
Yes, that's right. He was questioning how motion can be possible. And what he concluded, his paradoxes are meant to illustrate that, in fact, motion is impossible in some sense, okay? Or motion as one. You're right. I'm agreeing with you. Motion in our naive way of conceiving it, said Zeno, can't possibly be taking place, okay? So, of course, we know motion happens every day, but we have to be able to demonstrate what's wrong with Zeno's argument. Yes, that's our challenge, because we believe we're moving around. We believe things are moving around. But then if that's the case, then Zeno must have gone wrong somewhere in his argument. And so the challenge is to resolve Zeno's paradox, not by agreeing with him that motion is impossible, but by showing where he's going wrong in his reasoning. Okay, is that clear?
Yeah, that's clear. Thank you.
Good. Okay. So here is the first one. It's called the dichotomy paradox, or if you like, the race course. Sometimes it's called the race course paradox. And here's the paradox in a nutshell. I didn't share it. I'm sorry. I'm you've got me now, being the absent-minded professor. I put up the slide. That's the good news. The good news is the slide's up there, but I'm referring to it without sharing it. So, pardon me. I'm going to share the slide with you. Okay. And all these bells and whistles, these paradoxes are making me think too. So I forgot to share the screen. Here we go. Dichotomy. Everybody there? You see this, right? Okay. Dichotomy paradox. So he's saying the following. This is his first of four paradoxes of motion. So premise one, and this is if you want to run a race, or I'm just saying if you want to leave the room, okay? It's the same problem whether you want to run around a racetrack or if you want to leave a room, wherever you're trying to go, you have to get halfway, right? Does everybody agree that if you want to go somewhere, you have to get halfway there before you get the whole way? Is that fair to say? Let's take it a step at a time. Yes, I mean that's logic, right? Of course. All right, you're all agreeing with that. Okay, so far so good. Well, of course you have to get halfway before you can get the whole way. Sure. All right, premise 2, but wait a second, says Zeno. If you want to get halfway, you have to get a quarter of the way, because you have to get halfway to halfway. You're all agreeing you have to get halfway before you can get the whole way. But then if you want to get halfway, if that's like your sub destination, you want to get halfway, but you have to get halfway to that. So in other words, that's a quarter of the way, right? Of course. So before you can get where you're going, you have to get halfway. Before you can get halfway, you have to get halfway to halfway. That's a quarter of the way. And then premise 3, if you want to get a quarter of the way, of course, you have to get halfway there too, which is an eighth of the way. Yeah. And et cetera. So that actually problem is it never ends, because whatever fraction of the way you have to get to the half of that first before you can get there. That's right. Arsenello, is that your pronunciation? Arsenello?
That is right. That is
okay.
Right.
All right, Arsenello, good. And Nicole, so you're constantly being dichotomized because you're constantly taking half of a half, etc. means it never ends, right? That's the full word written out. ETC is the abbreviation, but it's how it's spelled, and so forth, etc. Conclusion: you can never complete all these steps, right? These steps are, in fact, an infinite series, and it goes on forever. You can keep dichotomizing till the end of time, and you'll never finish. And so Zeno says you can never leave the room. The conclusion is, how can you ever leave the room if you have to get halfway and then half of half and then half, etc.? You can never leave the room. That's his conclusion. Now, we know from our experience that that's ridiculous, because we can all leave the room, hopefully. Zeno hasn't proven that we can't leave the room. But what we need to do is to figure out how such a patently absurd conclusion fell out of an apparently reasonable set of premises. Okay, so Ahmed, you already have an idea why we don't think about the intricacies of the length of our destination of going somewhere. You're on the right track, Ahmed. Again, I like the intuition. Immediately, you've guided yourself into a fruitful avenue that will indeed lead to the resolution of this paradox, but it's a little more complicated than that. We have to make a very important distinction that Zeno either inadvertently blurred or perhaps he deliberately blurred. It's unclear to me. I think he may have inadvertently blurred it back then. Alejandro thinks he had too much time on his hands. Oh, you mean if he had spent more time on the beach, Alejandro, then he wouldn't have come up with these paradoxes? I don't know. Maybe you could use this. Maybe you could use this paradox to say you can never get off the beach either. You could use this as a justification to stay on the beach, because if you want to leave the beach, you have to get halfway, to the car or wherever you got there. So you could use it, cuts both ways. Well, Nicole, this is a good point also. You say you think he ignored time. In this paradox, we don't need time. We actually can afford the luxury of ignoring time. When we get to the arrow paradox, we cannot, because it also entails time. These are paradoxes of space and the division of space. So we don't need to worry about time in order to provide, let's say, a satisfactory resolution. All right. But I like your point about time. Time will become relevant in another of his famous paradoxes. In the meantime, we're only worried about the endless possibility of dividing space. Okay. Well, it doesn't matter about the language, Archinello. I mean, whether we're talking about a racetrack or a room or the room, or a specific distance that we're trying to, I'm assuming, and it's my clumsy wording, if you want to leave a room, it means you want to get to the door. Okay. So if you want to get to the door, this will all go through. Okay. So how did he get in? Well, so he's going to probably say he couldn't have gotten in either. Yeah. The problem clearly lies in reconciling this endless possible division and dichotomization, in this case, of space, with the notion that we know that if we take a single step, that we can traverse an infinite number of divisions, even with one finite step. And that's the key to the resolution. So this mystery can be looked at in the next slide as a representation of the actual series. Firstly, let's just look at the arithmetic, really, that Zeno is proposing to us. So let's say S is the sum of the steps that you need to take to get out of the room. And so he's saying you have to get halfway there. So this is, the distance you need to leave. So you have to get halfway there, then a quarter of the way, then an eighth of the way, right? Then 1/2 to the n. This is the series of divisions of the space. In fact, it's a geometric series with the constant ratio of 1/2 to the n between terms, where n starts at 1, which is 1/2, right? 2 to the first power. And then it never ends, because we can keep dividing, as we know. These increments can get smaller and smaller. It turns out, very interestingly, that this particular series actually has a finite sum. And so you see, it's already going to resolve Zeno's problem, but it's going to leave us with another problem, which is, how is it possible for an infinite number of things to add up to a finite number? That's another problem, okay, which is embedded in Zeno's problem. I repeat, this series never ends. Yes, we can arbitrarily write it out as many terms as we want, or program a computer to print out as many terms as we want, correct? There's no end to this, because n can increase without bound. And so it's never going to end. We're going to continually be able to subdivide into smaller and smaller decrements. But the thing is that if we actually want to know whether this adds up to something finite, and as we take more and more terms of the series, we get closer and closer to some upper limit or some upper bound on this set. In fact, it does have one, and it's pretty easy in 2 steps to show. Let's multiply this first line by 2, okay? So 2s is equal to 1 plus a half plus a quarter plus, you see what I'm doing, right? I'm just multiplying every term in the series by 2. This is what I'm calling high school math. So if we multiply s by 2, we get 2s, a half by 2, 1, quarter by 2, a half. Does everybody see that? That step clear? Okay. So actually, if you take a look now, what have we done? We've reconstituted s, right? 2s is therefore equal to 1 plus s, because 2s is 1 plus all of this stuff. All of this stuff, but all of this stuff is just s, all right? Multiplying everything by 2 just gives us 1 plus s. So if 2s is 1 plus s, well, then we just subtract s from each side and we get the answer. S is 1. So it turns out that this whole infinite series adds up to 1, which is a pretty amazing fact. Not every series is convergent or actually has an upper bound, but this particular series does. And that also is paradoxical, at least to me. This is not Zeno's paradox any longer. This is a question of how an infinite number of things could actually have a finite sum. But you can quite easily see that it does. And that means the closer and closer, the more and more terms we take, okay? Well, from S itself, rather. The more and more terms we take, the closer and closer we get to 1, but we'll never exceed 1, okay? The more and more terms we take, the smaller the difference between this sum and 1. Said a different way, but we never get to 1. And so here's another baffling thing, if you want to bring time back into it. And I liked whoever it was who brought up time. I forget who a few minutes ago was talking about time. You can look at this as a parallel paradox. It comes out of the same problem. Suppose it takes you a half a second to go halfway from the room, right? Half a second to go halfway. And you're traveling at a constant rate of speed. So now it would take you a quarter of a second to go the next quarter of a way. It would take you an eighth of a second to go the next eighth of the way. And it would take you 1/2 to the n seconds to go to the next 1/2 to the nth of a way. Does everybody see that? So in other words, it takes you a half a second to go the first half distance, and then a quarter. So after 3/4 of a second, you'd be what, 3/4 of the way out of the room, right? And after 3/4 plus 1/8, right, you'd be that much closer to the door, and so forth. So each one of these increments of distance could be transposed into an increment of time, right? So you're traversing each increment with an equal amount of time. So what's the problem there? Well, this is bizarre, because if you realize that there is no time, there is no particular moment at which you will have completed every step in this series. I mean to say, there's no instance in time at which all these steps, any particular step will have been reached in a certain time, but there's an infinite number of steps. So what I'm saying is you would need an infinite number of increments of time to complete them all. And yet, by 1 second, you would have done it. So we're saying you need an infinite number of increments of time to complete all these steps on your way to the door. And yet by 1 second of time, you would have completed all of them. Again, it's this notion of an infinite number of things being containable in a finite bundle, which is a little bit bizarre. And that's what I claim is the deeper problem that underlies Zeno's first paradox. And let me give you now a representation of how that gets resolved. And what we have to do is understand something that is not clear from his presentation, but which should be very clear from this diagram. And I think this will give us the resolution of the problem that we actually seek. Suppose we have a line called line 1. L1 means line, just a line, just a straight line, right? And line 2, okay, which is this L2 thing. And obviously L2 is longer than L1, okay? However you want to measure it, whether you want to measure it in inches or feet or yards or, the metric system, whatever. Line 2, whatever unit of measure you adopt, is longer than line 1. It's not an optical illusion or a trick, okay? So just first thing, interpret this. Let's say you want to go this distance, okay? And you want to go from the beginning of line 1 and walk to the end of line 1, all right? And suppose you wanted to go from the beginning of line 2 and walk to the end of line 2. It would take you longer at the same rate of speed, right? Since line 2 is longer than line 1, it would take you longer to walk the length of line 2. Does everybody agree with that? No trick there. I'm just saying it's a longer line. It'll take you longer to traverse it. That's common sense, yeah? Sure, it would. And it's the same thing, whether it's a mile or 2 miles, whatever the measure is, it's going to take you less time to traverse the length of that line at a given rate of speed and more time to traverse that line at the same rate of speed. Why? Because that line is longer, obviously. Okay. Well, here's the point, though. And this is the thing that Zeno has in a sense, hidden with his argument, is that although line 2 is demonstrably longer than line 1, the shocking thing is that they both contain exactly the same number of points. And what Zeno's really saying to us, I contend, is that the reason why we can't get to the door, or why we can't finish a race, or we can't traverse a given line of a certain length, is that there's an infinite number of points on the line. As we keep subdividing the line, we find we can subdivide it infinitely. And so we can never count all the infinite points into which we can subdivide the line, but that doesn't mean that we can't just take a big step and traverse them all, because the issue is that the interval of length is a very different measure from the number of points it contains. So we have to see, are we talking about apples or oranges, as the saying goes? If we're talking about the length of an interval, that is something we are indeed able to traverse. What we're not able to do is to count all the points we're traversing in the process, because of course they're infinite. And the sort of shocking thing, which was not demonstrated until Cantor did in the late 19th century, is the following: that every line segment, irrespective of its relative length, contains the same number of points, namely an infinite number. And this illustrates what the diagram now illustrates, that if we take these two lines, you can always do this with any two lines, L1, L2, doesn't matter their lengths. You can always align them, okay? Align one end of them together, and then connect those two lines, and then up to some vertex. You can always draw another line from their endpoints, connecting again, the endpoints and the beginning points, and you'll end up with a triangle. There always this construction, no matter what the lengths are, you can always draw that. So you end up with this triangle, right? And from this vertex V, draw a straight line, any one you like. Draw a straight line that cuts both L1 and L2, okay? And it intersects, specifically, it intersects L1 at X1 and intersects L2 at Y1. Now, every straight line drawn from the vertex down to, intersecting both lines is going to pick out two very specific points uniquely, right? Every line in red there, and you could draw how many? How many lines can we draw from the vertex that intersect both lines? Anybody? How many lines is it? Infinite, exactly, David. We can always draw an infinite number of lines from the vertex to, the intersect through both lines. And every one of those lines uniquely, this is the key thing, every one of those red lines uniquely picks out 2 points, X1 and Y1, yeah? So it doesn't matter that, this is the shocker, it doesn't matter that L2 is longer and maybe even twice as long, or it doesn't matter how much as long as L1, they still contain the same number of points, because every one of those infinite lines we could draw will pick out only 2 points, one on each line. And for every 2 points, they're therefore in a one-to-one correspondence. And so they contain the same number of points. Eventually, we could cover every point. In theory, we could cover every point we want to cover on L1, and we'll find that it corresponds to one and one only point, only to one point on L2. And therefore every pair of points here that we pick out is in one-to-one correspondence. So L1 and L2 contain exactly the same number of points, even though it's obvious that L2 is longer. That's what Zeno is actually hiding with his argument. So we could never get to the end of subdividing a line because the number of points is in fact infinite. But the interval that we can actually step over by taking a step is every time we take a step, whether it's a big or a small step, we are actually traversing an infinite number of points. But the very fact that we can traverse an infinite number of points does not prevent us from traversing a finite space. So Zeno's not saying that motion is infinite. He's saying that the interval, what we're actually able to do when we walk, is to cover intervals of finite length. But that each interval that we cover with each step that we take, in fact, contains an infinite number of points. But we never have to count those points in order to take that step. Why? Because intervals of a given measure, be they a foot or an inch or a mile, will always contain the same infinity of points. And we don't have to count those points in order to traverse that interval. And that's why we're able to leave the room. Okay, so in other words, the background assumption that we need to jettison is that the number of points that a line contains must somehow be proportionate to its length, right? And that the longer a line is, the more points it contains. If we're able to jettison that assumption and realize that every line segment contains an infinite number of points, that is, every line segment is infinitely divisible, but that does never prevent us from actually traversing the finite interval itself, even though it contains an infinite number of points, we can always step across the interval without worrying about the infinity of points. And that's how we leave the room. Is going to help you? Is this food for thought? I'm maintaining that that's the resolution of the first paradox, that every step you take, you're stepping over an infinite number of points, but that's never going to prevent you from leaving the room.
This paradox kind of connects to the race one, the one with the turtle and the fast runner.
That's the next one, Alejandro. How do you know about these things? Have you studied them already? By the way, that's a great question.
I already like looked over a lot of
oh, good for you.
Reading. I did the reading, and also I watched.
Well, I'm very impressed. All right, so that should make it simpler for you always if you do, the preparation. So yeah, we have 1 minute. I'm just going to pose the question. I'll answer it next day. There's a very definite answer to this one also, and maybe even a simpler answer, okay, as to Zeno's logic. but it's the next one we're going to look at in just a minute remaining. I'll pose the question, and then we'll answer it on Thursday in my breakout group, and we'll also look at the arrow paradox. So this is just to pose the question to you. I'll come back and share the screen. This is kind of fun. Everybody always sort of loves this one. It's kind of a fun paradox. It has to do with Achilles and the tortoise, right? So let me just share that. And here's a picture of it. There's lots of pictures online. So we know Achilles is a very fast runner, yeah? And we know a tortoise is very slow. So suppose they're running a race, and the idea is we're going to give the tortoise a head start. So here's the argument that Zeno makes. He says, okay, he's going to conclude that if we give the tortoise a head start, Achilles could never catch the tortoise. Why is that? Because we give let's say they're starting here together, and then we give the tortoise a head start to point B, okay, somewhere down the line. And when the tortoise reaches point B, Zeno says, then we let Achilles start running, okay? And so Achilles will eventually reach that point B, which we now call A prime. But by the time Achilles reaches that point, the tortoise will be a little further ahead, right? I mean, the tortoise has a head start, so it will take Achilles time. He'll be doing this much quicker than the tortoise. But when he gets to where the tortoise was at point B, the tortoise is now going to be a little further ahead at B prime, right? But Achilles is much faster. So Achilles is going to get there faster. He'll be at B prime quicker than the tortoise got there. And we rename that A double prime. But by that time, the tortoise is a little further ahead, still at B double prime. And when Achilles similarly gets to that new distance, where the tortoise is now, the tortoise will get a little further ahead. Now, of course, the tortoise's lead will shrink and shrink and shrink. So each time we look at the tortoise, he's less and less far ahead of Achilles. But nonetheless, by this argument, Achilles can never catch the tortoise, because every time Achilles gets to where the tortoise was, the tortoise is always a little bit further ahead. And by the time the tortoise catches that up, Achilles catches that up, the tortoise is just that much less further ahead. So on that argument, there's no way that Achilles can ever catch a tortoise. And of course, our common sense tells us that's absurd. Achilles, of course, is given the long enough race. It doesn't matter the head start, with the relative speeds. Achilles is going to eventually catch the tortoise. We know that, and we'll pass the tortoise. But then what's wrong with Zeno's argument? That's the real trick of this paradox, is to explain what's wrong with the argument, okay, that Achilles can never catch the tortoise. And that's what I'm going to leave you to ponder. And on Thursday, I hope you'll take that question up in your groups. I'll take it up with my breakout group Thursday. And also the arrow paradox, which you should definitely not try at home, because Zeno asserts that an arrow flying through the air can't actually go anywhere. So an arrow if somebody shoots an arrow from the bow, he says, that arrow can't possibly move through the air. And he gives an argument, also a very powerful argument. As I say, don't try that at home, because we know arrows fly through the air, right? So again, we'll work on that, and hopefully you'll all be working on that this week. Okay, you're more than welcome today. Thank you for your input. It's been really interesting. I'm glad I woke you up early with this stuff, but we'll be focused on the remainder of the two Zeno's paradoxes this week, and what we have to change in our thinking to understand them. All right, have a wonderful day, everybody. Have a great week. I'll see some of you on Thursday, and to be continued for us all next week with Anselm. Okay, bye-bye for now, and have a great day.